Okay, and then just one more quick policy, which is for questions. If you have a quick clarifying question, you should feel free to unmute yourself and ask the speaker, or you can type it in the chat and I can ask it for you at a convenient time. But otherwise, if they're sort of longer, maybe more substantive questions, it might be best if you hold them until the end, where we'll have some time for a Q&A. So with that, welcome to today's PRIISM seminar. We're delighted to have Professor Caleb Miles joining us, and Caleb is an assistant professor in the Department of Biostatistics at the Columbia University Mailman School of Public Health. He works on developing semi-parametric methods for causal inference and applying them to problems in public health and medicine. His applied work has largely been in HIV and AIDS, and he has more recently begun to work on psychiatric applications. His methodological research interests include causal inference, its intersection with machine learning, mediation analysis, interference, and measurement error. So we're really happy to have you, Caleb, and take it away.
Yeah, thanks again so much for the invitation, and again, feel free to interrupt with questions as they arise. So I'm going to be talking about optimal tests of the composite null hypothesis arising in mediation analysis. And this is joint work with Antoine Chamba at the University of Paris Descartes. So quick roadmap of the talk. I'll begin by talking about the problem setup, and I'll start with a little bit of background on mediation analysis, as I'm guessing that there are some folks who will not be too familiar with it. So I'll talk a little bit about kind of defining and identifying mediation effects. But really, the rest of the talk is going to be focusing on statistical inference, on the hypothesis testing problem that often comes up in mediation analysis. But if you're not someone who's interested in mediation, the statistical problem could arise in other places and be relevant to you. So from there, I'll discuss traditional tests of this null hypothesis and their shortcomings. Essentially, existing traditional tests of mediated effects are underpowered and overly conservative. And so that's what we're going to try to address. So then I'll present two novel optimal tests that we've developed. And then I'll briefly show some simulation results. And then I'll discuss an application of this new methodology to a real data example using data from this DCTRS database of randomized experiments with patients with schizophrenia. And then time permitting, I may get a chance to talk about p-values, which are kind of non-standard for these hypothesis tests. And then I'll wrap up with some discussion about other developments in the paper and some directions for future work. How could anyone not be interested in mediation? I agree, but not everyone does. Okay. So, quick mediation background, right? So in causal inference, typically we're interested in studying the effect of some exposure A on some outcome Y. And so mediation is kind of asking a more refined version of this question. In particular, supposing that there's some intermediate event that we think might be responsible for kind of transmitting this effect, right? So is A affecting M, and that change in M is in turn what's affecting a change in Y. So this is kind of the simplest DAG you could draw for the mediation setting. Mediation dates back to like the 1920s, like the path analysis work of Sewell Wright and linear structural equation models. So these traditional approaches to mediation actually define indirect effects or mediated effects in terms of regression coefficients. Traditionally, one would posit linear models for both M and Y, regressing M on A, regressing Y on A and M, and simply define the indirect effect to be the product of the A coefficient in the M model with the M coefficient on the Y model. And this has some intuitive merit, right? So beta 1 is kind of capturing the effect of A on M, theta 2 is capturing the effect of M on Y. And so kind of, really straightforward way of estimating the indirect effect is known as the product method estimator, which is just fitting a regression model and plugging in the coefficient estimates. So this is known as the product method estimator, is introduced in this Barron and Kinney 1986 paper. And this paper has like well over 100,000 citations and counting. So this is wildly popular estimator. So if you're a student of causal inference, then it should be fairly clear that there are a number of important limitations to this kind of approach. First and foremost, this has no clear causal definition, right? It's not in terms of counterfactuals. We typically don't like to just define something in terms of a parameter in a model and then claim it has some causal interpretation, right? It doesn't really make any attempt to account for confounding. Nowhere on this DAG have I included any confounders. And it doesn't allow for interactions, in particular between the exposure and the mediator, right? If we're interested in their kind of joint effect on the outcome, we would want to allow for the possibility that there are interactions so that we're not confusing mediation for interaction and other kinds of nonlinearities. So if you have, non-continuous mediator or outcome, you'd want to use like a GLM or something, right? Okay, so in 92, Robbins and Greenland, and in 2001, Pearl defined direct and indirect effects formally in terms of counterfactuals. So at last we have mediated effects with real causal interpretations. And I'm not going to get into all of the, even kind of the formal definition in terms of counterfactuals, just for the sake of time. But for identification, basically we need, so now I've added some confounders to our DAG here, right? So we have C here. So if C is observed and it controls for all of the following types of confoundings, the effect of A on M, the effect of A on Y, and the effect of M on Y. So if C is sufficient to control for all of them, and no component of C is directly affected by A, then the natural indirect effect, which is how Pearl defines an indirect effect, will be non-parametrically identified. So it's not tied to any particular parametric model or anything like that. So importantly, even if A is randomized, you still have potential confounding of the effect of M on Y. So you can't just, you're always going to have to worry about potential confounding in mediation. Okay, so this gives non-parametric identification. Okay, but we still need to estimate, models for M and Y. So, okay, so we could use linear models. So now these are the same as before, but now I'm just including potential confounders C in both of these models. And actually it's been shown that the natural indirect effect, when these are the models you use, is equal to this product of essentially the same product of coefficients, except now we have these C's involved that were, that this was defined in terms of previously. So that's kind of a nice result. And in fact, we can also include exposure mediator interaction. And now we'll have beta 1 times theta 2 plus the interaction. So I've added just this interaction here, the interaction coefficient between A and M. And so, of course, there are a bunch of other identification results available in the literature for other kinds of variable types and other kinds of models. And there are, semi-parametric approaches as well. So that's kind of the background on mediation. So we're going to focus on a particular kind of class of settings where the natural indirect effect is identified by a product of parameters. It doesn't have to be, right, this case here where it's beta 1 and theta 2, but effectively parameters, we'll call it delta X and delta Y, where these effectively characterize the effect of A on M, effect of M on Y. And these can be estimated in a nice fashion that I'll describe a bit more precisely on the next slide. And so this would also be the case for this exposure mediator interaction, where delta y would be θ2 plus θ3. Okay, and so we want to test the null hypothesis that the natural indirect effect is equal to 0. And so if it's equal to delta x times delta y, that's that this product is equal to 0, or equivalently, the null hypothesis that one of these, delta x is 0 or delta y is 0. So that's how it comes up in the mediation setting. The general problem statement that you might encounter in other kind of settings is, suppose that you have some parameters, delta x and delta y, and that you can estimate them consistently and with asymptotic normality. And importantly, that this asymptotic normality result is uniform in delta x, delta y. And I'll explain in a bit why the uniformity is important. And we want to test that this product, delta x, delta y, equals 0 with the nice properties that you'd often want from a hypothesis test, right? One, that it has at most 0.05 type 1 error for each delta x, delta y satisfying whose product is 0. So this is already, we see this is a composite null hypothesis. There are multiple delta x, delta y satisfying this. And then secondly, we want to maximize power in some sense everywhere else. So this is the kind of the general problem statement. Any questions so far? Okay, so next I'll jump into traditional tests and their shortcomings. Okay, so to kind of motivate the issue with traditional tests, here I'm showing a figure that's taken from Wang's 2019 Annals of Applied Statistics paper, and he is conducting an epigenome-wide mediation analysis. And so we can, I mean, these are for two different tests. We can just focus on one of them, say the one on the left. And so he's testing a whole bunch of null hypotheses of no mediated effects. And for each one of these, he's getting a p-value, this one according to a delta method test. And this is a histogram of these p-values. So in the case where, typically in the case where all the null hypotheses held were true, we would expect the distribution of p-values to be uniformly distributed. We would expect this to be completely flat, right? But in fact, what we're seeing is something much more conservative, right? We're seeing far fewer p-values less than 0.05 than we would expect. And this is for the joint significance test, similar story, right? So we're seeing these are both extremely conservative. So what's going on here? So we have Michael Sobel with us here on the call. So first I'll talk about what's often referred to as the Sobel test. And so in discussion with him, he's found the fact that this name kind of stuck somewhat perplexing. He says, well, I just used the delta method, which is in fact what he's done. So so he's just applied the delta method to this asymptotic normality result here in the mediation setting. This is a diagonal asymptotic covariance matrix. And so applying the delta method gives you a nice asymptotic normality distribution for the product estimator. And this will hold for all delta x, delta y, except for at the origin, when both delta x and delta y are 0. So when precisely one of these is 0, we get this test statistic, which I'll call z prod. So this is based on the product of delta x, delta y, will be approximately standard normally distributed. And so we can use this as a test statistic. However, something kind of strange happens when both delta x and delta y are 0. In fact, the convergence rate, we need to rescale. It's actually, the convergence rate is n rather than root n. And so this converges to a product normal distribution. So it's actually converging much faster at the origin. And so as a result, this test statistic doesn't converge uniformly in delta X, delta Y. So, you know, uniform convergence maybe sounds like kind of a technical concern. Why would we care about this, right? Well, often when we lack uniform convergence, it's kind of on the boundary of the parameter space in an area that maybe we don't care as much about. But in this case, we're actually kind of smack dab in the middle of the parameter space. Like if you were to put a prior on these parameters, delta X and delta Y, you would probably place the mode right there at the origin, right? So this is an important part of the parameter space. And so the practical consequence of this is that for any given fixed sample size, there's going to be a region around the origin in which this standard normal distribution that we're using as an approximation will in fact be a poor approximation of this test statistic. And in fact, this is easy to visualize. So here I've produced estimates of this z-prod statistic where I've fixed delta Y to be 0 and then varied delta X from 0 to 0.3. So the sample size 100. And I'm doing this a bunch of times to get a density plot for each of these, right? So the one in black here is the approximating standard normal distribution. And so we can see when we're at 0.3, you know, this is a decent approximation to the true distribution of the test statistic. But as we get closer and closer to 0, this is becoming more and more concentrated. So if we're basing our inference on the black curve, we're obviously being more conservative than we need to be. These test statistics are actually much narrower, or much more concentrated in their distribution. So that's the delta method test. So next I'll talk about what's often referred to as the joint significance test. And so the joint significance test, this has been shown to be the likelihood ratio test, excuse me, for this null hypothesis. And it's pretty simple. It rejects if the following both holds. It basically tests both of these null hypotheses separately, right? One is delta X is 0, the other is delta Y is 0. And so it uses the Wald test statistic for each of them. So, right, logically, if delta X times delta Y is non-zero, we need both of these to be non-zero. So it rejects if both of these reject, or equivalently based on the maximum of their two respective p-values. And so it's not really clear, but implicitly this is relying on an approximation that the minimum of the absolute value of these two Wald test statistics is follows a folded standard normal distribution. So I'm calling this test statistic Z-min. And it turns out when both delta X and delta Y are 0, this test has type 1 error of 0.0025. So it's also really quite conservative at the origin. And it also suffers from non-uniform convergence. So at 0, 0, this test statistic is not, this folded normal distribution is not going to be a very good approximation of the actual distribution of the test statistics. So we can do the same thing we did before. So here in black, we have the folded normal distribution. And then again, fixing delta Y to be 0, varying delta X from 0 to 0.3, we see that now we're doing a better job at 0.3 with the approximation. But again, as we get closer to 0, we get more and more concentrated distributions of these test statistics. Bootstrapping also doesn't work, sadly. And this is because bootstrap theory is known to fail when there's a discontinuity in the asymptotic distribution of the parameter space. So it faces kind of the same issues. So there have been a number of of simulation studies, kind of comparing these different approaches, and a few other ones that I haven't talked about as much, but these have mostly shown that the joint significance test has tended to perform best in practice. So that's kind of when we get to the simulations, you know, this is the one I'm going to be comparing against. Okay, so next I'll talk about our newly developed tests, but if there are any, you know, questions, I'm happy to take them. Okay, so our first insight was that, you know, we recognize we have this kind of problem with non-uniform convergence. And so we want to focus instead on the parameter space in R2, delta X, delta Y, because we know, or we're assuming, that the convergence is uniform in R2. And so there's going to be no discontinuity in the asymptotic distribution. Things are more nicely behaved. So the idea is to come up with a rejection region in R2 that's spanned by delta X, delta Y. So it's helpful to first consider, to go back to the joint significance test and visualize its rejection region. Right, so the joint significance test is testing separately whether delta Y is 0. So these horizontal bands give us the rejection region for that test, and then the vertical bands give us the rejection region for the test that delta X is 0. And so the intersection of the two is going to be the rejection region of the joint significance test. So these corners, right, are going out to infinity. And so we can see when the true delta X, delta Y is here at the origin, the probability of rejecting is, because this is the intersection, is going to be 0.05 times 0.05, right? Because we need both of these to reject. So that means that if we're thinking about rejection probability in the alternative space, right? The type 2 error being we fail to reject when we're actually in the alternative. So that's going to be 1 minus the probability of rejection in the alternative space. And if we're really close to the origin, that rejection probability is 0.0025. And so the worst case type 2 error is going to be very high at 0.9975. Where ideally we would want a test with worst case type 2 error 0.95, right? Because of the continuity of the rejection probability, we would want it to be 0.05, you know, exactly here. And so as soon as we start moving away from it, we get larger rejection probability. And so this idea is captured by the property of a hypothesis test that's known as similarity. So a similar test is a test with rejection region R such that for any parameters on the boundary of the null hypothesis space. So in our case, the boundary is just the null hypothesis space itself. It's these X and Y axes, right? The probability of being in the rejection region is exactly 0.05. That's a similar test. Excuse me. So in some recent contemporary work, Van Garderen and Van Giersbergen, these are economists from the University of Amsterdam. They give a result claiming that no similar test exists within a particular class of tests that's generated by a certain class of functions. So we were both kind of taking a similar approach, trying to come up with a function that would generate a rejection region in R2 satisfying this property. But we found that actually relaxing this class slightly, we are indeed able to construct an exactly similar test. And so as a consequence, we would have a minimax optimal test with respect to type 2 error. That is satisfying that the worst case type 2 error is 0.95. Excuse me. And so here's what our rejection region looks like. So comparing this to the joint significance test, it's exactly the same. These outer quadrants are exactly the same, but now we also have kind of these squares along the diagonal, and these are generated by a stepwise function that goes up kind of along the diagonal. So this looks like pretty unusual, right? So why does this work, right? Well, so you can think about, if we condition on Zxn, the walled test statistic for delta x being, say, 3, right? And if delta y is 0, then the probability of being in this vertical, in either of these vertical intervals, this is the 0.975 quantile, this is the 0.025 quantile. So the probability is 2.5%, 2.5% adds to 5%. If instead Z and X is like 1.9, we're here, right? This is the 0.95 quantile and 0.975 quantile, 0.25 quantile, 0.5 quantile. So again, the probability of being in either of these intervals is 0.05. And so the same holds everywhere along the x-axis. So marginalizing over this, we have the rejection probability. If delta y is 0, for any value of delta x is going to be 0.05. And then by symmetry, the same thing happens along the y-axis. And so we have a similar test. And so, I mean, just to reiterate, in case it's not clear, how this works is you would compute the walled statistic Zxn, compute the walled statistic Zyn, plot it in here, and if it's in the dark gray region, you would reject. Otherwise, you would fail to reject. And so the power surface corresponding to this test looks like this. So you can't really see the level curves. If we were in our studio, it would give me the level curves as I go along here, but the probability of rejection is exactly 0.05 on these axes. And then it goes up to toward 1 as we move away from the X and Y axes. Okay, so that's the minimax optimal test. So we also developed a test that's optimal with respect to a Bayes risk criterion, or approximately optimal. And so this was motivated by a 2014 JASA paper by Rosenblum and colleagues. And in fact, they're interested in testing a much different kind of hypothesis, but it turned out to be an approach that's quite amenable to our setting. So what they were interested in was a testing procedure for treatment effects in the overall population. This was in like a randomized experiment setting. So simultaneously testing for treatment effect in the overall population and 2 subpopulations. So this is kind of multiple testing problem. But we were able to kind of translate the idea to our setting. And so briefly, kind of the rough idea of this is, first, we focus on kind of a region in R2. And so we're going to focus on this region here, right, between about -4 and 4 by -4 and 4. So outside of this region, we're just going to say the test is going to be equivalent to the joint significance test. It's going to be equivalent to this one outside this region. And inside this square, we're going to define like a new rejection region. So first, we're going to start with the square, and we're going to partition it into a fine grid. And so that's going to generate a bunch of little cells. And for each of these cells, we're going to come up with a rejection probability. So the second step is we set up a constrained optimization problem for the rejection probabilities in each of these cells. So if you land anywhere in the cell, the rejection probability will be the same. And so the constrained optimization problem is 1, preserves type 1 error everywhere in the null set. So that's the constrained part. And secondly, it optimizes power according to some loss function in prior distribution on delta x, delta y. So we choose the 0, 1 loss and a bivariate normal distribution on delta x, delta y. And it turns out that this is a sparse linear programming problem, which is good news because we have a whole bunch of unknowns, right? If we have a fine grid, we have a bunch of things that we're trying to optimize over, but given the sparsity, it's actually computationally tractable. I can run it on my laptop. excuse me. And so this is what the rejection region ends up looking like. So in principle, this is a randomized test. So in each of these cells, we have a rejection probability. So the light blue is reject with probability 1, and the dark blue is reject with probability 0. And for the most part, almost all of these cells have exactly 0 or 1 rejection probability. There are a few where it's somewhere in between. The resolution, I guess, is not great when I saved it, but in any case, you kind of get the idea. And just some interesting things to note about that. I mean, again, we're seeing kind of an unusual, non-standard looking rejection region, right? We have these kind of like disconnected seeds in the middle. And also, I didn't impose symmetry on the optimization result. I could have and perhaps should have, but it's nice to see that it comes out almost exactly symmetrical. And we see that it aligns well with the joint significance test far away from the origin. And then towards the center is where things kind of start looking differently. So once again, right, you would compute your 2-wall test statistics, plot it here, and then whatever cell it lands in, reject according to that probability. You could come up with a deterministic test, just make it slightly conservative, round everything below 1 down to 0, right? Okay. So those are our novel tests. I'll move into simulations next. Okay. So for our simulations, we repeatedly drew IID samples xi, yi from a bivariate normal with mean parameter delta x, delta y, an identity covariance matrix with sample size of 100. And we're varying delta x and delta y jointly from 0 to 0.4. So this figure should really go out to 0.4, but you get the idea, right? So these are all the values of the delta that we're considering. So for each of these, we're gonna sample excuse me, 100 of xi, yi from this bivariate normal. And so here are the resulting power curves in these simulations. So I'm comparing the Bayes risk optimal with the minimax optimal with the joint significance test. And so we can see that, so the Bayes risk optimal and minimax optimal are sitting almost on top of each other here. Okay, so first, sorry, I should set up the figure. So we have delta ranging from 0 to 0.4 on the x-axis, and then the power, the rejection probability along the y-axis, right? And so the desired alpha type 1 error is 0.05. So we would want these to be at or below 0.05 at 0, right? And so we're seeing that this joint significance test is really conservative, right? It's well below 0.05, and it doesn't even get above 0.05 until out here, kind of past 0.15. And we see that our proposed tests dominate it in terms of power and still satisfy the type 1 error constraint. We see that the Bayes risk optimal has a little bit of additional power over that of the minimax optimal test for larger values of delta. It's not certain whether this is, Monte Carlo error. There's probably some, a little bit more power there. And then to a lesser extent, they kind of flip a little bit closer to 0 for smaller values of delta. So in any case, we see that these dominate this traditional joint significance test while still preserving type 1 error. Okay, excuse me. So next I'll talk about our data example. So we're using data from the DCTRS, or the Database of Cognitive Training and Remediation Studies, which is a collection of data sets from randomized experiments that are testing the efficacy of what's known as cognitive remediation therapy in patients with schizophrenia. And so cognitive remediation therapy, kind of I guess a little bit of the history behind this is that, traditionally medication has been used to target symptoms of patients with schizophrenia. but psychiatrists are also interested in improving patients' kind of functioning day-to-day outcomes, right? And so cognitive remediation it aims to improve cognitive deficits by teaching information processing strategies through guided mental exercises. So these are directly targeting cognitive outcomes, which are theorized to in turn lead to improvements in more distal outcomes like functioning occupational outcomes. Excuse me. And so this is a database of, I think at this point, maybe 16 or so studies, most of which are randomized experiments. One of the big challenges that I should say these results that I'm showing here are very much preliminary. There are certain challenges that we're not fully accounting for, but it is nice for kind of illustrating the methodology. So one of the challenges of this database that's not really related to the testing issue is that, you know, these coming from different studies, different studies measure different outcomes at follow-up. So there's a lot of there's a lack of overlap in variables that are observed at follow-up. So this is something that I'm working on developing new methodology for kind of separately. But in 3 of these trials, they do observe a common functioning outcome that we're interested in. So we focus on 3 of these. And so this consists of 142 patients with complete information on treatment, mediator, and outcome data. So in particular, A is our treatment. This is our treatment arm indicator, whether or not they were randomized to receive cognitive remediation therapy. Y is our outcome. This is a functioning outcome that's measured at follow-up by the social behavioral scale score. It's effectively measuring how well people function in terms of social interactions. And this ranges from, in our data, ranges from about 0 to about 53 or so. Our mediator is a measure of cognitive flexibility at the end of treatment. So treatment goes on, I believe, for about 3 months, and at the end of treatment, they do some tests to measure cognition. And so this is measured by the Wisconsin card sorting test, perseverance errors score, which is a measure of kind of working memory. This ranges from, I think, about 0 to around 100. And then for baseline covariates, right, this is a randomized trial, so we don't need to worry about confounding of A on Y, but we still need to worry about confounding of M on Y. And so our baseline covariates that we control for include sex, race, education, which of these 3 studies they participated in, and their baseline SBS and WCST scores. And so we're interested in testing the mediated effect of cognitive remediation on the functioning score through the cognitive score. This is kind of the theorized mechanism by which cognitive remediation is hopefully improving people's functioning outcomes. And so we fit the models, the exposure mediator interaction models that I showed previously. So linear model for the mediator, linear model for the outcome, but including the exposure mediator interaction. Excuse me. Oh, I forgot to mention, for both of the mediator and outcome, lower scores are considered better. And so the natural indirect effect, we use this plugin estimator that I showed before, and our estimated natural indirect effect is -0.4. So this this corresponds to a fairly modest improvement in SBS score due to cognitive remediation through the cognitive outcome measured at the intermediate time point. Okay, but is this significant? Of course, everyone wants to know. So we compare various hypothesis tests. So we compare the delta method, the joint significance test, the minimax optimal, and the Bayes risk optimal. And so for all of these, except for the minimax optimal test, they fail to reject, whereas the minimax optimal test does reject. So I haven't talked about p-values yet, but we have pretty large p-values for both of the traditional tests. We haven't defined it for the Bayes risk optimal test. And then kind of interestingly, we have a p-value corresponding to the minimax optimal test, which if you were to judge by the p-value, you would say don't reject. It's very close to 0.05. If I have time to talk about it, I'll get to that in a bit. But basically, there's not really a one-to-one correspondence between these two types of tests. And the way that we've defined the p-value is a little bit conservative. So if you were wanting if you're specifying a priori that you wanted to test this effect using the minimax optimal test, you would reject based on this test and not based on its p-value. But p-values are useful for controlling for like false discovery rate and this sort of thing. Okay, and so here are the plots of the bivariate test statistic in the context of the rejection regions of both the minimax optimal test and the Bayes risk optimal test. It's this pink dot here. So you can see it's falling in the rejection region for the minimax optimal test, but not the Bayes risk optimal test. And so that just tells us, right, these are different tests. They're not always going to agree. And so these effects are each of the corresponding effects, effect of A on M and effect of M on Y, are relatively small. And so it may well be the case that this is a type 1 error in the case of the minimax optimal test, but if it is, it's occurred with a probability of only 0.05. So we have controlled type 1 error. Okay, I think I have time to talk about p-values. Unless there are questions about the application first.
Can I ask just a quick question?
Yeah.
How easy is this to scale up so that other people can use this? Are these tests time consuming?
No. So we have software for the minimax optimal test. For the Bayes risk optimal test, there's some upfront cost to run the constrained optimization. But once you've done that, there's no need to run it again. So if you wanted to do the Bayes risk optimal test for some other value of alpha that hasn't already been run, you would need to run it again. But if you just want to do it for 0.05, it would be pretty much immediate. And so the minimax optimal test is extremely fast. So you can do large scale hypothesis testing relatively easily. The software is in kind of beta version. There are some improvements that we'd still like to make, but I'll share the link to the software at the end of the talk, and we're working on getting the Bayes risk optimal test implemented as well. Well, I don't know. I guess we're close to 11:50. Maybe I'll skip over p-values, and we can, if there's interest, we can cycle back to that, I guess, because I want to allow time for questions if there are any. I think the p-values are very interesting to me in the theoretical way, but maybe, yeah, anyway, I'll skip ahead. Okay. Oh yeah, so this is what I was just saying. We have an R package implementing the minimax optimal test. We'd like to incorporate the Bayes risk optimal test. It shouldn't be too much work in the near future. We also discussed tests of products of more than 2 coefficients. So this will come up kind of in path analysis or linear structural equation models when you have a path-specific effect through multiple variables. This will be kind of just the product of these regression coefficients. Unfortunately, these kinds of effects tend not to be identified when we start using the formal language of causality to define these path-specific effects. But this can come up in other settings where you want to test the product of more than 2 coefficients being 0. So for future work, I've started by saying, we're focusing on this setting where the natural indirect effect is identified by this product of 2 coefficients, delta x and delta y. But using other models for the mediator and outcome, or supposing you're interested in effects through multiple mediators simultaneously, the natural indirect effect will often be identified by like the sum of products of coefficients or the integral of products of coefficients. So we would like to generalize this to other identification formulas. As of right now, it applies to kind of the most commonly used estimators. Secondly, we would like to invert this test to produce better performing confidence intervals, but this is going to require extending this to other level sets of delta x, delta y equals k, where k is non-zero. So we'll have a much different kind of looking null hypothesis space. We'd also like to extend this approach to other settings that also suffer from non-uniform convergence. So an important example is, in partial identification bounds, which come up a lot in causal inference, these will often involve something like the minimum of 2 parameters or the maximum of 2 parameters. And this has a similar singularity when delta x equals delta y. So getting improved excuse me, testing confidence intervals for this sort of setting. And then further developments that generalize the p-value in tests of products of more than 2 coefficients, which we only are able to get into a little bit in this paper. So just some references if you're interested and would like to read more, some nice background on this composite null testing problem, or this McKinnon et al. Paper and Barfield et al. So Richard Barfield was my classmate we were in grad school at the same time, and he's the one who first told me about this problem, actually. And I've been kind of fascinated with it ever since. And so there are some existing solutions when you're testing mini mediation hypotheses. Wang, Dai et al. Recently in JAZA. So, I should mention, so all of the methods that I've talked about that we've developed apply to the case where you're just testing a single null hypothesis, but they also can be applied to large scale hypothesis testing, where you can just apply Bonferroni correction or Benjamini-Hochberg correction. So this problem is most evident, as we saw in the Wang figure, when we're testing mini and we can plot the p-values and see that they're non-uniform. But it actually is present when you're testing just a single hypothesis. The existing solution, so the Van Garter and Van Giersenberg paper gives a solution when testing a single mediator. They don't get an exactly similar test, but they get an almost similar test. And then the paper that we kind of adapt to our setting is this Rosenblum et al. Paper. And I have the bibliography here. If people are interested, I'm happy to share slides. But I'll stop here. So here's a link to the paper, a link to the R package, and then my contact information if there's any questions that you'd like to follow up with after the talk.
All right, well, thank you so much. I'll kind of clap on behalf of everybody. And let's open it up for questions. And as usual, I'd like to encourage any students on the call to, feel free to speak up and ask questions as well.
Well, if nobody, oh, right.
Hey, Caleb.
There.
Thanks for the talk. I have 2 questions, both of which may be naive, so please forgive me if they are. The first is, I was wondering if you could help me with the intuition as to why the rejection regions would be the diagonal instead of, say, arbitrarily large z-scores for one of the parameters holding the other one constant. The second question I have is, when I've been taught to think about these sort of testing for combinations of coefficients, one suggestion was to go to a Bayesian framework, and then you can generate the sort of distribution of multiple parameters or the product of parameters or the whatever through sort of Gibbs sampling. How does this approach compare to sort of that approach? Are they philosophically similar?
Yeah, I think neither of those questions are naive at all. I'll start with the second one because I think it's a bit easier to answer. So I think this kind of like, Gibbs sampling approach would be much more akin to kind of these traditional tests, which are right, are kind of taking functions of estimates of delta X and delta Y, compressing down to one-dimensional space where the convergence is non-uniform. So I imagine that this type of Bayesian approach you would end up kind of in the same place where you end up with approximations that are kind of poor. Although the other problem is that you have to be careful about, this is a composite null hypothesis, right? So you have to be able to control for type 1 error for everywhere in the null hypothesis space. So so you might have you might end up with a test that's good for some values of delta X, delta Y, but not for others. So yeah, regarding intuition, for the shape of this rejection region, yeah, it is like a kind of strange, surprising shape. The reason for this is that as you move away from the origin, so say you're out here, right? This is just the walled, if we just consider this, these horizontal bands as the rejection region, this is the walled test for delta Y being non-zero, right? And so there's, the further out here we are, the less probability there is near the origin. And so it's mostly just going to be corresponding exactly to the walled test, which is already doing a really good job far away from the origin. But it's when we get closer to the origin that we're going to start being more conservative, right? And so it's closer to the origin where we're lacking power. And so it's closer to the origin where we're needing to put more of our rejection region. And so the probability is, out here is of rejecting is 0.05, but once we get in here, if we're rejecting all the way out here, then we're now close to this Y-axis, right? And so we're now infringing on the type 1 error up here. So it's I guess the rejection region is kind of getting squeezed into kind of in between this kind of vertical band and this horizontal band. That's yeah, I don't know. Does that make sense?
I think so. Thank you.
Yeah, no problem. It's really that the kind of the problem area is central. So adding rejection probability farther away from it doesn't really help you much, and it hurts your type 1 error where it's already good. I think, I can't see names now, but we have a couple folks with the.
Should we do Jake and then Pat?
Hi, Caleb. This is really cool talk. Thanks very much.
Oh, thank you.
I guess I'm sort of, one is possibly naive question also, which is A is randomized in your applied example, and I'm wondering how important it is that it is randomized in terms of the reference distributions that you're using, and what you might do if A were not randomized. And similar kind of question comes up maybe on the M part, where maybe I'm wondering if your framework makes sensitivity analysis for the for C easier. So there's both questions are about A and M being not randomized, and how that matters either for reference distributions or for identification kind of issues here.
Yeah, good question. So, I mean, certainly these are important for identification. So in the example, there's no error from C to A here, right? So A is randomized, M is certainly not randomized. Otherwise, we would not be able to learn about the effect of A on M. If C does satisfy these conditions, though, then we have, where to go? We have our joint asymptotic normality result. So this assumption is crucial for identification. So it makes two of these assumptions automatic, which is always nice, right? The first two, right? It doesn't guarantee the third one, so we still need to control for C. But as far as the statistical inference goes, once we've identified, actually, this joint asymptotic normality is going to hold regardless of whether or not A is randomized. And sorry, was there a second part of your question?
The second question was about, if I understood you correctly, you kind of have this two-part test statistic, and of course sensitivity analysis for the C to M relationship is important.
Right.
You know, like I'm willing to grant the C to A relationship when A is randomized, but
right.
You know, so then we have to do something about C to M. So how do we, you know, so sensitivity analysis is an obvious approach. There's a bounds analysis as well.
Right, right.
But it struck me that maybe you've offered us an easier way to do sensitivity analysis.
I wish that were the case. Yeah.
Okay.
Yeah. I would love to say that, you know, we've improved both testing and provide sensitivity analysis, but no, we definitely depend heavily on C controlling for MY confounding. Yeah, it's not clear to me how you would. I guess I would have to revisit the sensitivity parameter, the form of it, and see. It's probably going to be more complex than this asymptotic relationship here. So I don't think that we could directly apply this. Maybe worth looking at. Yeah, thank you.
Okay.
Well, we don't have time for the question I was going to ask about your p-values, but I just want to say this is fabulous work, and it's really important for both medical sciences and for the area of psychiatry and psychology. People do randomized trials and then they try to interpret the results all the time. And as your example shows, the mediation allows people to really make a much better scientific statement about what has been manipulated. And it's going to be the case very often in practice that it's not as clear as they wanted. So the effects are going to be small. So your work is just really important because the small partial mediation effects are going to be common. Anyway, so congratulations on a really nice talk. It's really good work.
Thank you so much.
You both have very public emails, so you can email each other. Maybe Pat, maybe you can email Caleb with your question.
Yeah, I'd love to, to address your p-value question offline.
Great.
Is there no time for another question?
I think we probably have to wrap up, unfortunately. But maybe the best thing to do again is to connect offline. But since we have to wrap up, I'll just thank Caleb again for a wonderful talk, and hope to see many attendees at our next PRIISM seminar in a couple of weeks. So thanks so much, everybody. Have a good one.
Thanks again, guys.